Okay, so let's dive in. You're like buried in calculus homework, right? Limits, derivatives, all that stuff.
Hmm.
Now, what if I told you those same kind of abstract math tools could actually help you figure out the best way to cook your dinner, like tonight?
It sounds a bit wild, doesn't it?
Yeah,
But yeah, that's exactly the connection we found in the source material for this deep dive.
right.
We're looking at how these big math ideas, differentiation, integration, pop up in really practical places, specifically the kitchen.
And our goal here, pulled straight from the research we looked at, is to see how these math techniques can nail down the optimal cooking time.
But not just for taste.
No, for energy efficiency. You want to cook perfectly, obviously, but like without wasting power.
There's a sweet spot. And apparently calculus is the way to find it. It seems the energy used when you're cooking, well, it's not straightforward.
It's not just turn it on, use X amount of energy per minute.
Exactly. It's dynamic.
Right.
Think about the oven heating up, right? The heat escaping, the food itself changing as it cooks.
All that affects the rate energy is used and how much of that energy is actually doing the cooking.
The efficiency changes over time. So you can't just graph it as a straight line.
Okay, so this is where the calculus gets, well, interesting. The research modeled the total energy used over time, call it ET, like a function.
Right, ET.
Yeah.
But they weren't just looking at the total joules used. They wanted that most efficient moment to stop.
Considering, how cooked the food needs to be.
Precisely. And finding that moment,
Mm-hmm.
that's a job for calculus. Differentiation specifically.
Because that tells you the rate of change.
Exactly. Differentiating ET gives you E, the instantaneous rate of energy use. But the sources often look at an efficiency function.
Ah, okay. So maybe relating how done the food is at time compared to the energy spent getting it there.
You got it. Maximizing the output, the cooked food for the input, the energy.
And differentiation finds the peaks on that efficiency graph.
That's the idea. Take the derivative of that efficiency function, set it to 0, find the critical points. That's where efficiency might be maxed out.
So the sources actually did this. They didn't just theorize.
Oh yeah, they showed examples, like modeling an oven cooking something specific, and they found the rate efficiency improves. Well, it slows down.
It might even peak before the recipe says it's done.
Sometimes, yeah. Suggesting maybe a slightly different temperature or shorter time could save quite a bit of energy.
Wow.
And one paper even used integration, the other side of the coin, to calculate the total energy under different optimal cooking plans found using differentiation.
So they compared different scenarios. Okay, so the models included real physics, like thermal conductivity, heat transfer in the food and the oven parts.
Right. They needed that to build the energy function, ET, accurately in the first place. Then calculus helped optimize it. It connects the math to the actual cooking process.
So bringing it all together, we've seen how differentiation and integration aren't just abstract concepts. They can pinpoint optimal points for efficiency.
Even in something as everyday as cooking time to save energy.
And thinking about, food security and energy resources, making everyday processes more efficient, well, it matters.
It definitely does, which kind of leaves you wondering,
Yeah.
if calculus can optimize cooking, where else might these math tools you're learning be working behind the scenes?
Finding optimal solutions, making things more efficient in ways we haven't even thought about.
Exactly.
That's definitely something to chew on maybe next time you're looking at a derivative or just waiting for the oven timer. The connections are often closer than you think.